Recently, we've witnessed solar storms and auroras lighting up the sky, sparking both awe and curiosity. But what lies behind these mesmerizing displays? Today, we delve into groundbreaking discoveries from the ESA and NASA's Solar Orbiter mission that unveil the elusive origins of the slow solar wind. These findings are not merely academic, they have profound implications for how we protect our technology and understand our place in the cosmos. In this video, we'll dive into what sets the slow solar wind apart and reveal how scientists have unraveled its mysterious origins. So, without further delay, let's get started. For many years, scientists have been fascinated by the solar wind, an invisible stream of energy that flows from the sun. This stream has the potential to disrupt Earth's technological systems, such as satellites and power grids, in significant ways. It comes in two primary forms: fast and slow. The fast solar wind, known for its speeds of over 500 kilometers per second, springs from the sun's polar coronal holes, which are regions with open magnetic fields. But the slow solar wind, moving under 500 kilometers per second, has been more enigmatic, masking its origin and mechanisms from the prying eyes of science. This changed with the Solar Orbiter mission. Through a combination of high-resolution imaging and in situ particle analysis, researchers have pinpointed the genesis of the slow solar wind to regions where the sun's magnetic field lines open and close. These boundary areas, called helmet streamers, are characterized by their large, bright loops of gas that extend from active regions on the sun's surface. Periodically, these loops break and reconnect, a process known as magnetic reconnection, which releases solar material into space as slow solar wind. This discovery directly links the speed and behavior of solar wind to distinct parts of the sun's magnetic landscape. The implications of understanding where and how the slow solar wind originates are vast. It allows scientists to better predict the sun's behavior and its impact on space weather, crucial for future missions and satellite operations. Moreover, this knowledge refines our understanding of the sun's magnetic field that shapes the very nature of our solar system. Further insights into the slow solar wind were gained through observations of its temperature, density, and composition, which differ markedly from those of the fast solar wind. These observations suggest that the slow wind originates from more complex magnetic regions, where the sun's magnetic field is closed, forming loops that can trap solar plasma. These loops can become unstable and eventually break open, releasing trapped material as slow solar wind. This entire process is influenced by the sun's 11-year solar cycle, which affects the frequency and location of these magnetic reconnections. The ability to now track these slow solar wind streams back to their solar origins provides a new window into the dynamics of the sun's atmosphere. Scientists can observe changes on the sun's surface, such as the movement of magnetic fields and the evolution of active regions that lead to variations in solar wind production. This not only helps in predicting space weather, but also aids in understanding the fundamental processes at work in our nearest star, providing clues about other stars across the universe. Launched in February 2020, the Solar Orbiter is equipped with 10 scientific instruments that allow it to capture both images from a distance and direct measurements of solar particles and magnetic fields. This dual approach provides an unprecedented, detailed view of the sun. Central to the success of this mission are key instruments such as the heavy ion sensor and the magnetometer. The heavy ion sensor measures the composition of solar wind particles, identifying different proportions of elements like oxygen and iron between the fast and slow solar winds. The magnetometer assesses the sun's magnetic field in real time. Together, these tools not only determine where the solar wind originates, but also the conditions from which it emerges. This information is vital for piecing together the complex dynamics of the sun. Additionally, the Solar Orbiter's ability to observe solar phenomena like flares and coronal mass ejections up close offers insights into the sun's behavior during these intense events. The findings from it are challenging previous models of solar activity and are set to transform our understanding of the sun. the life-sustaining star at the center of our solar system. This orbiter's mission is particularly challenging due to the intense heat and radiation near the Sun. Engineers have equipped the spacecraft with a heat shield, capable of withstanding temperatures exceeding 500 degrees Celsius, allowing it to take measurements as close as 42 million kilometers from the Sun, which is closer than any previous mission. This proximity provides an unparalleled look at the Sun's surface processes and their link to the solar wind being studied. Understanding the slow solar wind has direct, significant implications for life on Earth. The Earth's magnetosphere, which protects us from most of the Sun's radiation, is constantly influenced by solar wind. Variations in this wind can cause geomagnetic storms that disrupt communication systems, affect satellite orbits, and even knock out power grids. By mapping the slow solar wind back to its sources on the Sun's surface, scientists enhance their ability to predict these solar events and better prepare for their impacts on Earth. This is vital for protecting our increasingly technology-dependent infrastructure, from satellites that manage GPS systems to power stations that supply our electricity. Additionally, these insights are crucial for broader scientific fields. They improve our understanding of how solar wind interacts with various planetary environments, which aids in assessing the habitability of exoplanets. This could further our search for life beyond Earth and inform necessary protective measures for future interplanetary travel. Moreover, these variations in solar wind influence the amount of cosmic rays reaching our atmosphere, which could affect cloud cover and climate. This connection underscores the importance of solar wind research in broader climatic and astrophysical studies. Thank you for joining us on this exploration into one of our universe's vibrant phenomena, the slow solar wind. Stay curious and keep looking up, for the secrets of the universe are vast and waiting to be discovered.